There's so much extra credit already.
Even though she hasn't answered mine in like 2 weeks.
Right, well, we have one more letter to finish on this problem. So what would part C say? You need part A, but this time, that sound like an echo.
Yes.
Oh my gosh,
I hate this thing. And I think the microphones in the ceiling aren't working. Okay, repeat part A, use torques about an axis. Let's see, let's do the plan. Okay, so let's kind of look at what that's gonna look like. We're just. Moving the pivot point down here. Okay?
I just, no.
Okay, so what we're gonna have to do in this situation. Okay.
Oh, my ears really pain. Good goal. Nice. Yeah, you look at it. It's out. But I'm gonna just sit by it.
So this time we have several torques to take into account. We have the torque of the man sitting at one point on the seesaw. Y'all are some dirty people. Okay, then you have, I'm not even gonna say that.
It's so weird.
Torque of the woman. Feels like we're naked.
Which one torques better?
Yeah.
Yeah, I'm glad you said it.
Here's the torque of the plank. And the torque of the pivot point. Okay, so. Based off clockwise, counterclockwise rotation, I'm gonna make you figure that out because I'm not repeating these. I can't repeat these, else we're gonna go through another 5 minutes of torque jokes.
I promise that was my only one for the rest of the day.
Come on, just
So of course, the man is at a distance, so if we put the pivot through the very left end, the man is at a distance of 1/2 L plus that extra X. The woman. What position is the woman? Right, so. 0.
Wait, the MG plus 0 is that the torque of the woman is less?
Yeah.
Oh my gosh, okay. I'm actually being curious.
So you have the mass of the plank. Gravity. And that center of mass is at 1/2 L.
Can we do this in lab yesterday?
Kind of, and then the torque of the pivot is the normal force at 1/2 L. So we're still we're just thinking the seesaw is still sitting on its original pivot right in the center. We're just like, what happens to these torques if we then move a rotation point down to the very far end where the woman's at? Okay, so No, no, no.
Liam asked me what it was yesterday. And I showed him.
Liam's the one who looked it up on YouTube.
Why he asked me what it was yesterday.
Oh. Yes, that meme was the burnt peanut. You guys,
Yes.
the streams, they're chaos and they're absolutely wonderful. Okay, so we need to figure out what the normal force is. Okay, so we can plug that in. So then what we're going to need here is the sum of our torques. Let's see.
You watch on the street.
E over 2.
How I was, I had. And snack type of pieces, but when I would eat something, it'd make me nauseous.
Okay,
Crazy.
so see, we're still trying to figure out what X is in this case. They all have the same denominator, so we can say we can reduce down to reduce this a bit further. So that's what you would solve to. And then when you plug all your numbers in, you find out that X is still at 1.46 meters. Really? I'm going to take it off and put it down here and hope it catches enough of the sound. Well, and I don't like hearing the echo through the speakers.
Those cheese curls.
Does everyone have this copy down? Okay, now we're going on to equilibrium and biomechanics. You what?
What do you mean?
Allegedly? Yeah. Allegedly. Just trying to be diplomatic, allegedly. So I put this diagram in here. This is something that you want to start working on if you're going to have to use biomechanics. You have force, so like you see the force supplied by the muscle. But you see them that force supplied by the shoulder. So keep in mind, every time a muscle pulls, you're going to get a back force from the joint. Because that muscle is going to pull on the joint, it's going to shove the joint, it's going to pull the joint together. And then the shoulder socket is going to push back with another force. Okay. So. All right. The person is allegedly standing with their arm outstretched in a horizontal position, holding a weight of 9.9 newtons in their hand, 60 centimeters from the shoulder. The weight of the arm is 30 newtons and its center of gravity is at 27.5 centimeters from the shoulder joint. The deltoid pulls on the upper arm at an angle of 15 degrees above the horizontal and 12 centimeters from the joint. What is the magnitude of the force exerted by the deltoid muscle on the arm? Now, we don't actually need that force of the shoulder. So let's go ahead and draw this in a way where it's a little more basic. So we'll put your pivot point there. That's going to be your shoulder joint. With your arm, and then out here at the end. Mass. There's the weights, gravitational force. Then we're here about the center of mass. With the force of gravity of the arm. Of course, we said this is your axis. That's your shoulder joint. Let's see, then you're going to have the force supplied by the deltoid. Phi, that angle phi. That's your 15 degrees. So then let's start taking account of our various distances. We know this one is 60 centimeters. That one's at 27.5, and then the force. That is going to be at 12 centimeters. I do apologize, this is not to scale, so. Because we're just worried about the force of the deltoid pulling on the arm right now. We could calculate that back force of the shoulder, we're just not asked for it at the moment. I put this diagram in here because any of you who are gonna have to use stuff like this, you always need to realize that the joint is gonna put a back force, is going to supply a back force based off muscular contraction. It's also like, if you ever calculate it, it's also a good thing to realize that this is why your padding in your joints breaks down. These forces can get pretty large. Okay, what is the magnitude of the force exerted by the deltoid? All right. So we have an equilibrium system, so let's just start with. I feel like I don't have the link right. I have this thing in my way. TED Talk microphone. Okay. Let's start looking at all of our torques. The torque of the deltoid. Torque of the arm. And torque of the weight. Again, another reason we don't have to worry about that back force is the back force is supplied right at the axis, so it's not going to supply it, it's not going to provide a torque. What if you wanted to?
What if it wanted to?
Okay, well, then that means that your arm would have to be rotating at some other place than your joint.
Sounds comfy. Oh, bargain.
I think at that point you have bigger problems.
Another joint.
Work on your arm.
It's okay.
Good idea. How about Reagan?
I mean, maybe if you were Mel Gibson in Lethal Weapon, your arm could be rotating from different locations, but. Yeah, see that face, you know what I'm talking about. Okay, so. Okay, so here's my question. Which of these are gonna be positive, which ones are gonna be negative?
Aren't they all gonna be positive because they're all going like, no, they're all being negative, you're doing clockwise.
Well, look at the force of the deltoid. Its torque will produce what kind of motion? Clockwise, counterclockwise?
Counterclockwise.
Counterclockwise. So that one's positive, the other two are negative. Okay, let's start thinking about what these torques are. So torque of the deltoid is going to be the force of the deltoid that we're looking for. Position of that torque. Sine of phi. Torque of the arm. Force of gravity of the arm. The position of that force. And the torque of the weight, going to be the gravitational force of the weight, position of the weight, sine of theta. And of course, with both of these, what does theta equal? 90 degrees, because that force of gravity, if you're holding your arm straight out, it's truly level. That force of gravity is going to be make a 90-degree angle with the arm. So the sine of theta in both cases is going to reduce to 1. Okay, so what we're going to end up with force of the deltoid, position of the force, sine of phi, force of gravity of the arm, its location, force of gravity of the weight, its location equals 0.
What did you say? Oh, no.
I don't know.
I'm scared.
Either.
Mine's not in yet.
Hey, we're trying to figure something out here. We don't need to know how badly you failed in another class. Are these like your first grade to the semester or something?
Even looking in class is brave. I would wait until I got home in case I needed to cry.
What class are they looking at?
Okay.
Oh, heck yeah, dude.
Good.
But,
Fourth of the deltoid.
This is a valid crush that I had. Yeah. Cause I had 400 crush out. Just the screaming in my car was kind of, I was so.
And so this is where we would get to before we start plugging in numbers. Now, in particular, this section, I really hope our PT majors are paying attention. Also, kind of important for our wrestlers. You could actually do the math on how to get an advantage.
During the match.
I would do it before the match.
No, I know.
Like I would find out height, weight, all kinds of situations about your opponent, start planning accordingly. Because you can start flipping opponents with minimum effort. Not quite, it's not quite the Deadpool way, because, you know, Deadpool's always maximum effort, but still.
Of course. Still long calculation.
Okay, once you plug, so let's plug these in. So what? Gonna be 30 newtons. So notice I've changed the centimeters to meters.
You guys are still.
Go out of your campus and go back.
The force that the deltoid has to supply is gonna be 456.9 newtons. Now, someone, so this is a good lesson. So someone look up for me. So the here is 9.9 newtons. Give me an idea of how much that, how many pounds that would be.
It's 85.
No.
I guess.
Because like
You guys
55,
remember how to use Google, right?
well, 55 newtons is like 112, so not that much.
So 9.9 newtons is really, really low. Someone tell me about how many pounds of force you're gonna need for that 456.9.
Lot.
Yeah, but the point is,
I don't necessarily care how it's, if you. Yeah, it's just you would on. Just, like, I prefer not to know. I think at least deserve.
So basically, do you see how much force that the shoulder muscle has to supply for a relatively small weight in your outstretched hand?
See, I knew it and I still got.
It's a lot of
That's my issue.
Yeah, so 9.9 newtons.
Um,
I was just like, she's.
400.
102.7 pounds of force.
At the shoulder?
I don't know, that's what Google told me.
Wait, it's only like 2.
Yeah, so about 2 pounds in your hand leads to over 100 pounds of force necessary in the shoulder. And you wonder why when you go to the gym, you get tears, you get injuries, so you can see just how much,
You're telling me not
I mean-
to wait.
it's like 50 times the amount of force at the shoulder than what you're holding in your hand. So,
That's not even that much.
yeah, no.
It's
That is like,
overthinking everyone should put.
Yeah, anytime you're in the gym and let your ego get the best of you, you're gonna tear something.
It's so strange though, she's not saying trust me.
Well, that's why I don't work out.
It's
Science
just, oh, I
fact.
ever thought like.
Science.
What,
I feel you there.
It's just like a bad.
Working out's too dangerous, man.
Science supports that we really shouldn't, apparently.
Yeah, science supports you going to hurt yourself.
a science that says it's
I
good.
go to genetics and she's like, working out is good.
No, and that was my
You're-
issue, 'cause
you're
I was like,
are
It
you gonna
is
bring?
actually
why
don't
should
hold
we
your
just
voice
say
volume.
flipping?
Well, I don't know, maybe genetics and physics don't agree.
Maybe it's just because it says the full. Number. So it's like this.
Oh, exactly. And then I was like, but it makes some stars. I was
How
like,
about we have a 50
just
newton
was like-
bowling ball in a person's hand with their, okay. So what you're thinking about here is a person's arm is right at their side. They're not holding the bowling ball like this. I don't think anyone could do that. It's like right here.
You can do it, it's just hard, really, really hard to do this, but you don't bowl like this, but you can do
Bring in a bowling ball. You're gonna come up in front of the class. You're
it.
gonna,
Six, what?
you're gonna hold it like this.
Yeah, there's 8.
Hey, you should ask Peyton, Peyton's a pro bowler, my sister.
I don't have 8-pound bowling balls at my house.
I love how you're making us all very, very aware of things so we can.
Yeah, you might be scared. Peyton's
Properly
here.
torture her.
Right, the thing is, in bowling, they say you have to be able to hold your bowling ball out like this for you to be able to throw it, and if you can't, then it's too heavy.
Huh.
At least that's what somebody told me when I was little. And it's
I
done.
think that someone was just feeding you a line. Because bowling has to do with your swing, with the angular momentum. And so once you get the momentum moving, you use quite a bit less strength. So yeah, I think somebody was just making that up.
It's the guy that literally drills bowling balls, so I don't know if he was actually making that up.
Well, drilling holes in bowling balls and.
A really complicated science, actually.
That is my new profession, is drilling.
I still think he was making it up.
Well,
Said that.
believe what you want, but who's the professional here? Not you.
Swing arm and your momentum. Okay, anyway. Your forearm's horizontal. It makes a perpendicular angle with your upper arm. Now, see, your bicep muscle is attached at 0.03 meters from the joint. And the ball is 0.35 meters from the joint. Find the upward force exerted by the bicep on the forearm. The downward, so this one we're gonna do this. The downward force exerted by the upper arm on the forearm. So again, you're gonna hold the bowling ball. You're holding it up. You have the bicep producing a force to hold the ball up. Your joint is producing a back force that's going down. We're gonna figure out how much that is. So this time, we're actually even gonna neglect the weight of the forearm. We're just gonna say, well, we could incorporate the torque of the forearm, but let's just leave it out in this case because it's gonna be minute compared to the other torques. Okay, so. There's your upper arm. Follows your pivot point.
How do we know we have it at 90 degrees?
says the
Horizontal, upper arm is vertical.
Oh. Well, I didn't read. When have you done slow?
Bowling ball. Okay, so. What are the forces that we know are present? Okay, we know that. The bowling ball is gonna have a downward force, so its weight,
And I'm pretty sure I have this up.
weight of the bowling ball.
You too? I forgot to respond.
The force of the bicep.
He's probably gonna eat dinner by then.
And then. I'm gonna call this force here. I'm gonna call that R because it's a reaction force. You know, we have a distance X there between where the bicep actually pulls and the elbow joint. So we're going to consider that force of the bicep to be going straight up because the angle that it's at is extremely small. So we can approximate it to be going straight up.
Reaction force.
So again, you have your muscle, it's going to pull your arm up. And as you do that, your bones and your joints are going to interact with each other. And so then your joint is going to, as you pull this way, your upper arm interacting with your joint is gonna produce a force going down.
So is that different from the back force?
No, it pretty much is the back force.
So what's this, force B? Is that what that is?
Oh, force of the bicep.
Oh, bicep, oh.
Yeah. We have the weight of the bowling ball, force of the bicep. R is your reaction force or your back force based on the force produced by the bicep. Okay, so. We know that X for the bicep pull is 0.030 meters.
Pretty sure.
Now is 0.350 meters.
I'm just training.
Okay, so just for some reference,
Never.
your 50 newtons would end up translating into about a 9-pound bowling ball or about a 10-pound bowling ball,
11.2, the internet said.
11.2.
Yep.
No, when I Googled it, it said like 9.9. Well, we'll go with one or the other.
I put 50 newtons to pounds and Google said that equals 11.6.
Either one. Huh? No, that was 9.9 newtons.
I think like 2 pounds.
Yeah, it's like 2 pounds. Okay, so
No,
again, it's an equilibrium system. So the sum of your torques, torque of the back force, or the reactive force, torque of the bicep force, torque of the bowling ball equals 0. Okay, now that back force is R. It's at a position, it's right at the joint, so that's going to be 0. There's no torque from that. Force of the bicep,
Yeah, I don't see anyone.
sine of theta.
Maybe D.
Bowling ball. L. Sine of theta. Now for both of these, what does theta equal? So the sine of theta is going to reduce to 1. Oh, let's see, when we solve this, we want to solve for the force of the bicep. We're going to get the weight of the bowling ball times L divided by X. When we put our numbers in, the force of the bicep, 583 pounds. Wait, no, 583 newtons, sorry. Which would translate to about 131. 131 pounds that the bicep's going to have to exert on the either 9.9 or 11.2 pound bowling ball. So again, you see just how much greater that force has. The force has to be by the bicep just to lift what we think is a light weight.
reaction force. The one of our straight arm, did we have reaction force for that one?
We did, that force of the shoulder that you saw, that would have been the same one. We just didn't calculate, we just didn't need to calculate it for the last problem. So if you go back up.
I can see him.
Yeah, it would have been this one right here.
And this is consistent.
Yep. So now how do we figure out what that back force is? Okay, so we've done our equilibrium system of torques. What do you think we can do now to figure out what that R force is?
We just do this on.
We can, yes. still equals zero because it's an equilibrium system. So minus R plus the force of the bicep minus the weight of the bowling ball. Zero. When we solve for R, we get the force of the bicep minus the bowling ball. And so R is going to end up being 583 newtons minus 50 newtons. R is going to be 533 newtons.
36.
If we want to translate this to pounds, it's about 140 pounds. So think about that. So you see, okay, first off, who would consider, I don't know, let's say, when I Googled it, it said 9.9, you said 11.2. Let's go somewhere in the middle and say 10.5, okay? How many people think curling 10.5 pounds is heavy? Yeah, nobody does. But then let's look at what happens to your elbow joint. So first off, your bicep's going to have to produce a force, right to, yeah, I mean, it's very clear you take steroids. But so your bicep is going to have to start to produce a force right at about 131 pounds. Then the back force on your joint, when your bones interact based off moving that 10.5 pound bowling ball, when your upper arm and lower arm, those joints interact, your upper arm is pushing back on your shoulder joint at about 121 pounds. Are you starting to see why injuries happen? You're just weak. Yeah, no matter how much you work out, you cannot increase the strength of your cartilage.
Why not?
Which is why, like in weightlifting, why do you think pec tears are one of the most common? Because what you have guys trying to bench press like what, 200-300 pounds? And that entire weight is going to be based off the fact, I mean, yeah, your pectoral muscle is large, but its only major attachment is this tiny little tendon that attaches right to your shoulder. So you're having to transfer all that force through that tendon into the larger muscle. So yeah, you tear the crap out of that tendon. So I don't care what genetics says, working out's bad for you. Well, true.
It's different. You should
Checkmate.
drink your milk.
Checkmate. You're gonna keep working out, no osteoporosis. Okay.
I feel like there has to be a medium here, like, to bench press at 300 pounds.
There is. I know working out's good for you, but physics makes you go, I don't want to do it.
Well, my 10-year-old brother can throw a 10-pound bowling ball, so I'm not worried.
Well, there are a lot of other processes that come into play in the body when it moves, but it's just kind of letting you know what's happening in your joints based off, various motions and forces that you're going to exert on your body.
Yeah, because when that back.
Man. It's kind of crazy to watch.
You're like, no, I felt that before.
Tweets.
All right.
30s.
Rotational form of Newton's second law.
Feet are out of clean. It's like eighth rep.
Scary.
So now we have what? This is our third expression of Newton's second law. Sum of the torques equals I times alpha.
Dances back.
Okay, what was I?
Yeah. You can see
Yeah, that's why we didn't.
Moment of what?
Inertia.
Inertia. Alpha is, so what's alpha?
You hate me so much.
Yeah.
Oh, shit.
I didn't really.
Yeah, just a kind little warning. Don't ever try to make Sonia feel guilty. It's not gonna go well for you.
Rotational acceleration.
Yep, rotational acceleration. Okay, so how do you think we get to this expression?
I get a 0 in.
Slide told me the one equation has the most.
Well, okay, well, let's just start with our original expression of Newton's second law.
Slide told me so.
Okay, so we know that.
Okay.
Now, let's do a cross product with R on both sides, okay?
Thank you. Never go. Bench, big climb bench. Flat bench, you carry your back a lot easier. Yeah, what we do is, we do smart though, because it's percentage. Ever eagle, really don't ever eagle that flat bench. Exactly so.
You like Dr. Everett?
Yeah, I really felt that.
I don't care if you do it here.
Does anyone remember Grumpy Cat? Yeah, that was a good one. Okay, so now we have this cross product on both sides. All right, so the first, let's go now and kind of get a graphical view of what we're looking at here. Have you ever drawn a circle so bad that your iPad thought it was a parallelogram? Get this.
Completely snaps.
There we go, that'll work. Okay, now. Imagine we have rotation like that. We have a radius R. Now we know at each individual point, we're going to have a linear acceleration. And we remember that R and the linear acceleration, the tangential acceleration are going to be perpendicular to each other. And then based on this, which way does our angular acceleration vector form? Remember how we found it?
Nope, okay, not gonna get it. Does it have to do with counterclockwise or?
You don't remember how we found it?
What?
No, okay. So you look at your rotation. And so you take your fingers and you wrap them in the direction of the rotation. Your thumb's going to point in the direction of your acceleration vector.
It's like left-handed and right-handed candy.
That's going to be your acceleration vector. Okay, so we'll bring back a couple of equations that can help out. So linear acceleration is R times alpha. Okay, so now we're going to go back to our expression up here. So we know that R cross F is torque. On the right side, we're going to get R cross M times alpha plus R. Because we can translate it can be like that. Okay, so now we have two cross products here. Let's start to break this down. So we're going to have R M alpha R sine of theta 1
Hilarious.
and sine. So we're going to get a sine of theta for each cross product. Okay. Now, looking at the graphical representation, what do you think theta 1 and theta 2 are? What do you think they are? It is, what about theta two?
Since he graduates this year. So he's like.
They're both 90. They're both gonna be 90.
His line. That was funny.
So what we end up with, sum of torque equals the sum of MR alpha.
He's also.
What is the sum of MR?
This would been here a while. He just didn't get a start. Ratio.
Sum of mass times radius. What is it? What is it? It's a physical,
No, he wasn't doing
quantity, physical quantity. It is the equation for what? Nope.
Ethan.
Yeah, it's probably the.
Ethan Leak.
Yeah,
Brody. Brody.
that's your moment of inertia.
Leak over. He likes secrets.
So you see, we can start with the original expression of Newton's second law. We can end up now at this rotational definition of Newton's second law based on torque. Okay, so you'll be happy to know we've run out of time.
Yes.
So we will continue with this on Monday. So what I plan to do to end the semester is we're going to finish this chapter, do chapter 9, which is fluids, and then go to chapter 12, which is sound.
4 weeks?
Keep in mind, more than half of one of those weeks you're gone because of Thanksgiving break.
Today.
Yeah.
Giving turkey.